This is the APC 2-5 instantaneous velocity lecture. We have we studied average velocity, and now we're going to be studying what instantaneous velocity is. We see that it's really the same thing as average velocity, but you're finding the slope of the line at a point, not over a long period of time. When you do this, when you look at the slope of a line, or a slope of a curved line right at a single point, you're really looking at the slope of the tangent line to that point, and this is also called taking the derivative of the function. The derivative looks like this. We're saying here that instantaneous velocity v, this variable, is equal to the limit of delta x divided by delta t as the t approaches 0. So we're coming to a very small, infinitesimally small period of time. And that whole idea, that limit, is rewritten as this, the dx over dt. So our equation really is velocity equals dx over dt. We're going to look at a sample problem right now, sample problem 2-2. This is from the textbook. Below is a distance versus time plot for an elevator cab that is initially stationary, then it moves upwards, which we take to be the positive direction of x, and then it stops. What we want to do is plot the velocity versus time graph. So I'd like you to right now pause the video, and on a sheet of paper or in your notebook, draw this position versus time graph, just sketch it, and then you're going to sketch a velocity versus time graph. So pause the video now, and once you start the video up, and actually what you're going to do is you're going to look at the slope of each point along this line, and you'll notice down here at point A, down at this position, the slope of that line is 0, so we know the velocity is 0 right there. So then you go ahead and look at the slope of that line, you look at the slope of the line up there, you know the velocity is 0 again. So your velocity versus time graph is going to look something like this. And you'll notice over here at point A, the slope is 0, and way over here at point D, the slope is 0, or the position, the velocity is 0. So at points A and D, the velocity is 0. And you'll notice that between B and C, the velocity stayed constant, and that's because between B and C in the distance versus time graph, you had a straight line. Then you'll also notice from A to B, the velocity is increasing, and that's back at the other graph. You'll see that between A and B, this line is curved, that this line right here between A and B is a curved line, so the slope is always changing. That's why in the next section, the next graph, this velocity right here, this section here, the velocity is always changing because in the previous graph, the slope was always changing. And then the same thing happens over here, except it's changing in the opposite direction. We're going to take a look at derivatives. The first question is, what if we were given a position function instead of a graph? Well, if we're given just the function and not the graph, in order to find velocity function, we would take the first derivative of that position function. So we start off with a displacement function or a position function, take the derivative of it, take the first derivative, it gives us the velocity function. So this last sentence says the first derivative is used to show the slope of a function at any point. In this case, it represents velocity. We take the first derivative of a position function or a displacement versus time function, you will get velocity. Sample problem 2-3. What we're going to do now is take a look at a position versus time function or a x versus t function. So that we have the position of a particle moving on an x-axis given by x equals 7.8 plus 9.2 t minus 2.1 t cubed. X is in meter, t is in seconds. What is the velocity at t equals 3.5 seconds? Is the velocity constant or is it continuously changing? So I want you to pause the video now, find the velocity function by taking the derivative, and then what you'll do is you plug in the 3.5 seconds for your time. So pause the video, do that, and see if you come up with the same answer we have here. So that we'll have the next slide. So now that you've done this, we'll check your answer. We have our position versus time function. We take the derivative of it. comes out to be 9.2 minus 6.3 t squared. We then plug in 3.5 for our t value, and our answer ends up being a velocity of negative 68 meters per second. Now the question was the velocity constant? Well, it's not constant because every time you plug in a new time, the velocity is going to be different. So our velocity never changes. Our velocity is always changing, and the time is changing. Okay, let's wrap up 2-5. We first saw that instantaneous velocity can be found by finding the slope of a position versus time graph, or by computing the first derivative of the position function. And that is the basic idea of 2-5, is this wrap-up idea.